Good afternoon, everyone. Welcome to my talk. I want to talk about the coupling of partial differential equations, PDE, to simulate flow problems. The work presented here was finished by myself and my collaborators. First, I'm going to talk about motivation and background. Then, using a model equation to tell how we do coupling. Then I'm going to go to coupling of flows. First, compressible flow, incompressible flow, then cold ocean flows. Finally, conclusion. Let's see background and motivation. Here I give 3 examples. Each of them shows the need to couple PDG and their models for their simulation. The first one on the left here is oil spill in Gulf of Mexico happened in 2010, long time ago. Some of you might still remember it. Okay, the event started as a plume, oil plume or jet from a broken pipe at the bottom of the ocean. Then oil reached the water surface, become a very thin layer of oil floating on water surface. Horizontally, the floating oil was a few hundred miles, huge. And at the bottom of the ocean, the jet here is much smaller, like 10 meters in scope. So it is a multi-scale phenomenon. And the phenomena-wise, pattern-wise, they are different, so multi-physics. Currently, we have PDE-based computer models to simulate such a flow, like the plume. We also have a different model to simulate the oil patch. However, so far, there is no single model, computer model, which can simulate both of them simultaneously and also together. However, this is a single event. Start from the bottom of the ocean, then reach this water surface. So we need a couple PDE, their PDE, and their models for better simulation. Right. So other 2 examples tell about a similar story. Now let's see how we do coupling. Here we have a advection diffusion equation in subdomain omega 1, and then we have another advection diffusion equation in subdomain omega 2. The 2 subdomains overlap in this region, and the solution of the 2 subdomains are exchanged at x1 and x2, which are called interface. We first transfer this PDE into algebraic equation, then formulate the computation problem as a linear algebraic problem. This one here. Okay. In computation, we compute the 2 equations in subdomain first, then exchange their solution at the interface. After exchange, you compute the 2 subdomain again, then you exchange again. So keep doing this way. So basically, it is a iteration, right? So this iteration is called Schwarz iteration. And you all know for iteration, a key issue, a fundamental issue, is if the iteration converges, or how fast it converges. So for explicit schema, if we apply explicit schema in subdomain, then the problem can be formulated this way. We can derive a sufficient condition for convergence. This is just an example. If implicit scheme is applied in subdomain, meaning we need to compute a linear algebraic system in each subdomain. This way, we can also derive convergence speed in this way. Convergence speed here is actually contraction rate. Okay. When we compute this problem using traditional methods, meaning we directly exchange the solution at the interface. And the convergence usually is very slow, meaning we need many time of iteration to reach a final convergent solution. So a key issue is how to speed up the convergence. Here I present a methods like this way, which has two parameter. So this is a optimized interface condition, which has a specific value for alpha and beta, like here. We prove the contraction rate will be 0, which is the best you can hope, meaning convergence will be reached by 1 or 2 iterations only. So this is the main result we obtain on this part. Let's see how does this optimized interface condition work. So here are 3 examples of computation by traditional methods. You can see they converge, the residual becomes lower and lower with regard to this iteration number. Then if we apply optimized interface condition, here you have 1 or 2 iterations here, then quickly drop to this convergent solution. I mean 0, it's about the 0 convergence here. So convergence is reached by 1 or 2 iterations. This is from linear advection diffusion equation. If we apply the optimized interface condition to Burke's equation, which is nonlinear, you can see here the property of quick convergence by the optimized interface condition still there. Okay. In some situation like this to here, the optimized interface condition needs many more iterations. Okay, that reaches convergence. Here is about the 25. It's many more than 1 or 2. However, in comparison to the line here, these are traditional methods. So the optimized interface conditions are still much faster. Okay. Okay, so this is the model equation part. Let's go to comparable flow. First, comparison flow. This situation has PDE. PDE is going to be Euler equation. So we have actually 3 equations of PDE here. When we compute or couple those PDE into subdomain, at the interface, there are 2 methods to exchange solutions. The first one, probably you can imagine, we just use interpolation. This is called a non-conservative interface scheme. The second one is a conservative interface algorithm. Here I don't talk about detail, but it can guarantee numerical solution to satisfy certain property, like a conservation or conservation of flux at the interface, which is a property of PDE themselves. So conservative interface algorithm is sound in theory. Okay. Let's see how it performs in computation. So we have 2 subdomain here. So there's an interface in between. There's a vortex moving towards the right, pass interface, and go away from interface. So when we apply conservative interface algorithm, this is the solution. So there's almost no distortion of the vortex. There's no artifact. So this is the beauty part of the algorithm. What happens if we apply non-conservative scheme? So here I gave 2 examples, but I just talk about this one. In this case, the solid line is the exact solution. A shock wave is moving towards the left here, and another one is moving towards the right. So by non-conservative interface algorithm, solutions are in red. You can see at this location, shock wave is computed at this height. However, it is only this much. So there's a big error in strength of a shock wave. On this side, the solution, numerical solution tells shock wave is someplace here. But however, it is actually here. So location-wise, there's also error. So this will be big problem in computation of realistic problems. So when we apply this conservative interface algorithm, solution are in blue, then you see accuracy it becomes much better, right? However, in practical computation, in realistic problem, non-conservative scheme, namely interpolation, is widely used simply because it is straightforward and easy to implement. And then we wonder if there's a mathematical foundation for this. So we proved this a long time ago. A conservative scheme is good as long as it satisfies certain conditions. So here is an example. There's a wave, shock wave, propagating towards the right, passing this grids. So here is a solution. As you increase the mesh resolution, the solution becomes even better. Okay, so this is just evidence showing it works. So this part is what I want to talk about, the compressible flow. Then let's look at the incompressible flow. Suppose we have two subdomain, blue and red. Navier-Stokes equation are applied to both of them, and the equations are coupled at the interface here. So this is a numerical solution. Here shows there's a vortex shedding generated and separated from a cylinder. This is a cylinder, actually it's here. And you may pay attention on the solution along the circle, which is interface. So you can say solution structure trans across the interface smoothly without artifacts. And here shows the comparison between the results of a coupled PTG and the results obtained by some other methods, including experiment. Overall, the comparison as well, this shows the coupled PTG work very well for this problem. And here is the flow in reservoir. In this reservoir, there is a thermal stratification, meaning on the top there's a warm of water. And furthermore, in this reservoir, there's a sort of a fish. They tend to stay in warm water on water surface. Later, a project was built here, like this one. They want to just collect fish from water surface by this structure. And after collecting, fish will go down here, then finally go to downstream of the dam. Before construction, they want to make sure after the build of this structure, the stratification of thermal temperature is still there, so they can collect the fish as they want. So we made the computation of the temperature flow using coupling of the PTG. Here is the computed temperature distribution. Blue, low temperature, red, warmer water. So you can see temperature change with time. However, hot water or warm water stay on the top. So with this regard, their design is good. Finally, I'm going to talk about the coupling of a flow in ocean. So basically, this part is a Navier-Stokes equation. This part is PDG for ocean flow. So we couple them in two ways simultaneously. So the two models march in time simultaneously. Here, there's no time to talk about the detail, but just give final results, show how it works. We have a surface wave coming from a left towards the right, then climb the beach, impact a cylinder inside here. This cylinder. This part is ocean PDG. This part is a Navier-Stokes equation. And as this is simulated results. Green in color is the water. So you see water moves. Okay. As the water passes the cylinder, it impacts the cylinder. The computed force by water on cylinder is this green line. And the red circles are from the experiment. So you see they match very well. In this situation, we consider climate change and sea level rise, because people are becoming more and more concerned on safety and the vulnerability of a cold structure like this house. So we'll make a simulation on this. Basically, we put this house at the front beach, someplace here. Here is New York. So we assume there's a tsunami at the deep ocean. Then the tsunami is propagating towards the seashore and climb on beach and then impact house. So we made the simulation using this coupling. Here is the simulated results about the flow to pass this house. And here show you detail of the flow at the house. These are simulated force acting on the house in XYZ direction. And this video show you the process of the flow pass impact the house. In this example, we consider thermal discharge or hot water discharge from a bottom ocean from this pipe in 1 meter in diameter, and it has a few ports from where hot water is discharged. Because the tides flow, ocean flow goes forwards and back. So the plume here, simulated plume, is going forwards and back. This video basically show you the process. Those red lines here are interface between ocean PDE and the Navier-Stokes equation. So here you can see how the plume, simulated plume, pass the interface. So basically, you don't see obvious artifact and interface. That's a good sign for us. Okay. I have been presenting many successful examples just now. However, you can imagine the coupling is not easy, especially when we talk about the flow. Their PDE are complicated. When you couple them, it is becoming more difficult to solve, to simulate. So we face a lot of problems and challenge. So here is one example. This flow coming this way. Red one is a subdomain, and the blue one is another subdomain. So you can see the solution for the red one already arrived here. It's fast on the top, but at the bottom, the solution from the blue subdomain does not respond immediately or simultaneously. Apparently, this is kind of a non-physical or error. In this part, flow goes to right from a red subdomain. Blue subdomain gives you flow coming back. So again, this is non-physical. This blue line here is an interface between two subdomains, between PDEs. So here are solution contours. You can see there's a lot of accumulation of contour of solution along the interface, which is an artifact, numeric artifact. So those are difficulties. They affect the solution of accuracy. They affect the reliability of a numeric solution. So we want to get rid of this. We are working on this, and hope we can get some results, make progress on this part. Then conclusion. You see, coupling of a PDE has many application backgrounds about the flow problems. Actually, it is well beyond the flow problems, maybe in your area also. And also, coupling of PDE is most feasible and the most promising approach to simulate a multi-scale, multi-physics problem. We also see there are many problems and challenges, so we need better mathematical foundations and also better computational methods. Okay, this is the end of my talk, and I would be happy to take questions. Thank you.